Chemistry has a built-in paradox. The reactions that define our physical world happen between individual, microscopic atoms, but human beings can only hold, weigh, and measure continuous, macroscopic clumps of matter. For centuries, chemists working in the laboratory were restricted to observing bulk physical properties. They used tools like this antique balance scale to measure the mass of a substance, with no way to count the particles reacting inside it. To predict how a reaction would behave, they needed a mathematical bridge, a way to translate the mass of a single atom, measured in atomic mass units, directly into the grams they could actually weigh on a scale. That translation mechanism is the mole. A mole is exactly 6.022 times 10 to the 23rd entities of a given substance. This specific value is known as Avogadro's constant. To understand the sheer scale of this constant, imagine the Greek god Zeus counting atoms. If he started at the Big Bang 15 billion years ago and counted 1 million atoms every single second, he still wouldn't be finished today. He would need another 4 billion years just to count a single mole of atoms. This grouping of such massive magnitude is a physical necessity. Because atoms are vanishingly small, the mole provides the exact scale required to translate chemical reactions into quantities we can actually see and measure. By standard definition, 1 mole is the exact number of atoms found in precisely 12 grams of pure carbon-12. This specific baseline was chosen because it creates a locked mathematical relationship between the microscopic atomic mass unit and the macroscopic gram. We can see this in the math. 1 atomic mass unit is equal to 1.66 times 10 to the 24th grams. When you multiply that tiny fraction by Avogadro's constant, the output is exactly 1 gram. Because these two values perfectly cancel each other out, the mass of any single atom in AMU is numerically identical to the mass of 1 mole of those atoms in grams. If a single oxygen atom weighs 16 AMU, a mole of oxygen atoms weighs 16 grams. 19th century chemists like Stanislao Cannizzaro painstakingly standardized these relative atomic weights. Their work proved that if you knew the mass of a substance, you could calculate the exact number of particles inside it. For decades, the mole was tied to a physical artifact of carbon, but in 2019, the International System of Units redefined it. The mole is now permanently fixed to the exact numerical value of Avogadro's constant, untethering it from any physical object. Grounding the mole as a fundamental constant of nature guarantees 1 mole of carbon contains the exact same number of atoms as 1 mole of lead. It provides a permanent 1-to-1 baseline for comparing completely different materials. When elements react, they follow a balanced chemical equation. This equation dictates strict integer ratios of interacting particles, like 2 atoms of hydrogen combining with 1 atom of oxygen. The equation strictly requires particle counts, ignoring physical measurements like grams or liters. To use these equations in a lab, chemists rely on a theoretical routing hub. Here, the mole acts as the central node, connecting the particle ratios of the equation to 3 measurable macroscopic pathways: mass, gas volume, and exact particle count. Following the first path, you can convert physical mass into moles by dividing your laboratory grams by the specific molar mass of the substance. Moving to the second path, you can measure gas expansion. At standard temperature and pressure, which means 0 degrees Celsius and 1 atmosphere of pressure, 1 mole of any ideal gas occupies precisely 22.4 liters. Dividing a total volume by 22.4 routes you right back to moles. And on the third path, you can calculate the absolute entity count by multiplying your moles by Avogadro's constant. This hub establishes the cardinal rule of competitive stoichiometry. You can never directly compare the mass of 2 different reactants to determine which one is in excess. Because elements possess different atomic weights, 100 grams of a light element like hydrogen represents nearly 50 moles of reactive particles. 100 grams of a heavy element like lead represents less than half a mole. The mole acts as a universal translator. It strips away misleading properties like mass and volume to reveal the true mathematical count of reacting particles. Moving from theoretical rules to industrial application, we can look at the Haber process. This is the primary method for synthesizing ammonia on a massive scale. We can apply the routing hub to a classic limiting reagent problem, the kind of advanced stoichiometry required in competitive exams like the JEE. Look at the balanced chemical equation. One molecule of nitrogen gas reacts with 3 molecules of hydrogen gas to produce 2 molecules of ammonia. This operates like a locked mechanical gear system. One turn of the nitrogen gear strictly requires 3 full turns of the hydrogen gear. Now, imagine a problem gives you a starting inventory of 2,000 grams of nitrogen gas and 1,000 grams of hydrogen gas. The immediate cognitive trap is to look at those numbers and assume that because there is only half as much hydrogen by mass, the hydrogen will be the first reactant to run out. We process the data by pushing the 2,000 grams of nitrogen through the routing hub. We divide the mass by nitrogen's molar mass of 28 grams per mole. The output is 71.4 moles of nitrogen. We execute the exact same step for the second reactant, pushing the 1,000 grams of hydrogen into the hub. We divide by hydrogen's molar mass of 2 grams per mole. The output is 500 moles of hydrogen. Now compare the raw outputs. We have 71.4 moles of nitrogen and 500 moles of hydrogen. Translating the bulk mass into moles instantly shatters the illusion created by the raw data. It reveals the true operational inventory of the reaction. With the inventory converted to moles, we can identify the limiting reagent. The limiting reagent is the reactant that will be entirely consumed first. It acts as the strict mathematical bottleneck that dictates exactly when a reaction must halt. We take our 71.4 moles of nitrogen and apply the 1:3 gear ratio from the balanced equation. This shows a strict requirement of 214.2 moles of hydrogen to consume all the nitrogen. We then compare that exact requirement against the actual hydrogen inventory we calculated in the previous step, which was 500 moles. We only need 214 moles, but we have 500. The hydrogen is in massive excess, meaning a large amount of it will be left completely unreacted. This confirms that nitrogen is the true limiting reagent. Once those 71.4 moles of nitrogen are gone, the reaction stops. Nitrogen will solely dictate the final product yield. By applying the 1:2 product ratio from the equation, the 71.4 moles of nitrogen limit us to generating exactly 142.8 moles of ammonia product. This is our theoretical yield. Finally, we route those 142.8 moles of ammonia back out of the hub through the mass pathway. Multiplying by ammonia's molar mass of 17 grams per mole yields a final measurable mass of 2,427.6 grams. Predicting chemical outcomes is impossible through mass alone. The limiting reagent can only be unmasked by operating exclusively within the mole domain. This routing logic extends far beyond isolated and industrial reactions. Advanced exams frequently test your ability to navigate multi-step, multi-phase laboratory setups. A typical scenario might require you to react an impure solid powder with a specific molarity of aqueous acid, molarity being a measure of concentration in moles per liter, to capture and measure an evolved bass. The primary trap in these problems is cognitive overload. It is easy to become mathematically lost when you are forced to juggle solid mass percentages, liquid solution concentrations, and expanding gas volumes simultaneously. Your defense mechanism is to isolate the mole, treat it as the single conserved token of exchange that passes unbroken through every phase change and reaction step. Whether a substance exists locked in a solid lattice, drifting as a dissolved ion, or expanding as a heated gas, its fundamental mole count remains the absolute, unbroken thread of logic cutting through the chaos of the system. We have traced the mole from the cosmic scale of Avogadro's constant down to the hyper-precise calculations of industrial chemical yields. Formulas like mass divided by molar mass provide the physical translation between the macroscopic world we touch and the microscopic world where the reactions actually occur. This quantitative architecture is what empowers chemists to confidently engineer the physical world, predicting exact macroscopic outcomes from invisible atomic interactions. Mastering the mole routing hub provides the ultimate heuristic for surviving competitive chemistry exams and executing real-world chemical engineering. The mole stands as the definitive bridge of metrology. It is the quantitative architecture that makes chemical science possible.